Hi everyone, my name is Cameron Batchelor and I am an App State Geology alum. I graduated in 2015 and I am here recording this video today because I have lots of experience using mass spectrometers and I wanted to share with you all some of what I've learned. So this is just showing you the context of my background. I've worked in 3 different labs, UNC, Minnesota, and Wisconsin, each with different mass spectrometers. So I look forward to sharing with you all my experiences. So, really, this technique is a way to answer the question, what is the abundance of isotopes in a specific material? And you might be wondering, why would we even ask that question in the first place? Well, answers to this question include telling us about the age of certain materials. For example, how old is the oldest rock on Earth? Also, it can tell us about what types of environments rocks and minerals are forming in, such as was there liquid water on ancient Earth back during the Hadean, when Earth is thought to be one giant ball of magma. Further, we can disentangle past climate conditions back millions of years. For example, how wet was North Carolina 1 million years ago? We can use mass spectrometers to measure the abundance of isotopes in materials and answer these questions. Before I dive into the specifics of mass spectrometers that I've used, I wanted to go over a basic diagram of the structure of a mass spectrometer. So over here is where we put our sample into the machine. We have a heat system above that vaporizes the sample, and below we have an electron beam source, and essentially this source knocks off electrons from the atoms in our sample. And by knocking off electrons, we're giving them a charge, so we're ionizing them. Once they become ionized, they can accelerate through this electrical field where they enter in a magnet. The magnet is really important because it's going to affect the angle at which our ions are deflected through the chamber. So the strong pull of the magnet is going to cause this. And for a given charge, the force of this magnetic pull is going to be the same, but what affects the different angles that you see here in this diagram is actually the mass of the ion. So an ion with a heavier mass is going to be less deflected than an ion with a lesser mass, which is more easily deflected down. And therefore, based off their mass and the angles at which they're deflecting, the detector down at the bottom of the machine is actually counting the amount of times heavy versus light isotopes are hitting our system. So if we have more heavy isotopes in our sample, the detector is going to count a higher abundance of heavier isotopes than lighter. So it's all dependent on this magnet bending our ions based off their mass and charge. All right, now I'm going to get into the mass spectrometer that I've used extensively for my PhD. This is the Wisconsin Secondary Ion Mass Spectrometer, or the SIMS. As you can see, with 2 people for scale, you can see it's a very large machine. It pretty much takes up the entire room. And what's unique about this mass spectrometer is that we are able to measure spot sizes from 1 to 10 micrometers. So this is a very, very small sample size and allows for the precise measurement of isotopes across a very small space. Just to orient you with the structure of this mass spectrometer, so over here to our right is the sample loading station with the loading wand off to our right. Below is the electron beam source, which is actually a cesium beam that knocks off the electrons from our sample. It is then accelerated through the chamber here until hitting this black box, which is our magnet with the 2 red things sticking out. This magnet deflects our ions based off their mass into the detector located back here to the left of this person. This is our sample workstation, so we can actually receive results live as the isotopes are hitting the detector, and so we're able to assess our data as we make these measurements, which is pretty cool. Okay, just to give you all an example of the live data that comes in as we make measurements on the SIMS. This is an example from a session I ran back in June where I'm measuring oxygen isotopes on a cave stalagmite sample. In this column, we have the file ID number with the associated sample name. These 3 columns are showing the oxygen isotope data as they come in live. And I will just note that for every 20 measurements that we make within our sample, we have to make 8 standard measurements. So in blue here, above and below this sample bracket, you're seeing the measurements of the oxygen isotope values in a calcite grain of known value. So we know this calcite grain has an oxygen isotope value of 12.5. Therefore, based off how the machine is measuring the oxygen isotope value of the standard grain, we're able to calibrate the oxygen isotopes of our sample. So this is a necessary step of the SIMS. Every 20 measurements, we make 4 more standard measurements. You can also see there's much more information the mass spectrometer is providing us, such as the XY location of our sample measurements. So within our mount, so this is the coordinates of each oxygen isotope measurement. And this way I can go back and make sure all the measurements are in stratigraphic order. In addition, it gives us the date and time. Based off this, you can get a good idea that it takes about 2 to 3 minutes to make one oxygen isotope measurement. So within a single day, we can make several measurements as shown here. Another thing to keep our eye on is the IP column, or intensity primary. And so this is basically telling us the intensity of our cesium beam, which is our electron beam source that is knocking electrons off of our particles. And remember, that's really important because the more electrons we knock off, the more we are going to accelerate through the mass spectrometer and make our measurements. And so if the IP dips below a certain value, we actually have to add cesium into the source reservoir to ensure that there are enough particles being accelerated through our mass spectrometer and the yields stay high enough to make accurate measurements. So this is an important column to keep our eye on as we make SIMS measurements. Now I'm going to quickly walk you through what exactly I'm putting in the mass spectrometer to measure. So as I mentioned before, my project is reconstructing climate conditions in the Midwest, specifically from a Wisconsin cave. So what you're looking at here, this is a cave stalagmite from that Wisconsin cave. And if you cut open a stalagmite, you can see that there are these distinct growth layers, which I'm pointing at here. And each one of these growth layers represents a different year, let's say, of growth, and therefore a different isotopic signal of the rainfall during that year. And rainfall can tell us about the temperature, and we can also learn about rainfall amount from the oxygen isotopes within rainfall. So by measuring the oxygen isotopes down this stalagmite sample, I am able to understand what climate was like back hundreds and thousands of years. So first thing is I cut and I polish my sample, and what you're seeing here on these dots, these are hand-drilled oxygen isotope measurements that I made essentially with a dental drill, but we can ignore those for now. But because the SIMS measure such small scale, so remember those 10 micron analysis pits, I need to cut the sample to be a very small chip. So here I am slicing it. And you need to cut it even more. So here I've sliced it again, and my target area is down the central growth axis, so right up the sample, and I've highlighted in this box exactly where I want my targeted area. So once I get those slivers, I can mount them on a very small epoxy mount. So this is about 15 millimeters in diameter. So here are my 2 sample slabs, which respectively are here and here. And you can see these white grains down the middle. This is our standard calcite grains that we measure, because in order to make these measurements, you need to calibrate your calcite measurements to an accepted standard. So that's what you're seeing in the middle here. Okay, I'm just going to put everything together for you all and show you the power of the SIMS. So on the left here is a stalagmite sample from a Wisconsin cave that I'm analyzing for my PhD, which is why you can see I've sliced it respectively, because I will be analyzing it on the SIMS. So more specifically, here's my sample mount. And just to orient you all, this is a spatial database, so everything I show you is to scale to this ruler on the right. So here is the sample mount for this specific stalagmite sample. You can see the 2 chips, and then in the middle here, these tiny grains, if you can see them, these are our standard calcite grains that I mentioned back when I was going over the spreadsheet. So these are the standards that we measure about every 20 times we measure our sample. So to show you the power of the SIMS, this is a white light image of our sample chip, and these tiny black dots are where the SIMS is measuring oxygen 18. So each one of these tiny circles is about 10 microns in width, and it represents one of the oxygen isotope measurements that I make on the SIMS. So you can see how fine of a scale I'm able to measure oxygen isotopes in this sample. And just to relay the importance of the fine scale to you all, I'm going to show you an image of fluorescent banding within the stalagmite sample. So what you're looking at here are essentially annual cycles of rainfall within the stalagmite sample. So you can think of the bright green bands as representing heavy rainfall periods, so essentially the summer season, while the darker bands are periods when there is not as much rainfall, so it's the rest of the year. So each time a bright band bounds one of these dark bands, this is a 1-year cycle. And so I am interested in reconstructing seasonal patterns of climate back thousands of years, which is only possible with the SIMS because if I overlay this transparency, you can see with the SIMS I'm able to fit multiple pits within single fluorescent bands, which wouldn't be possible. So here you can see I fit 3 oxygen isotope measurements within this bright green band, and then several during this dark period. Once again, several pits within this bright band with several in the dark. So perhaps I should, there we go, that's more obvious. But you can see this is only able to be done with the SIMS, and if we were to drill this sample by hand, I would essentially be averaging several of these different seasonal cycles, which is not what I want. So this is the great power of the SIMS and why I feel very fortunate to be able to use it for my PhD. Okay, just to drive this point home, on the left here, I'm showing you a stalagmite sample from my Wisconsin cave with the respective fluorescent banding in green and black. And on the right, on the x-axis, we have delta oxygen 18 isotopes with the depth on the y-axis. And these black points are where I measured oxygen isotope data by drilling the sample by hand using that dental drill that I mentioned earlier in my video. So you can see this record overall is very coarse in resolution, whereas in yellow here, these data are showing where I measured oxygen isotopes using the SIMS. So these tiny black dots on the left here, and I've circled them in yellow. So overall, you can see I can fit several SIMS measurement points in between individual conventional oxygen isotope analysis pits that I drilled by hand. So this is a very high resolution tool that we can use to resolve high resolution climate records going back thousands of years. All right, I just want to conclude by letting you all know that the SIMS is actually responsible for giving us the oldest known fragment of Earth. So this is Professor John Valley. He is the PI of the WISC-SIMS lab, and here he is measuring a zircon grain from Jack Hills, Australia. And this zircon provided us with the oldest known age of a rock fragment of Earth because the SIMS was able to measure the core. So as you can see, this is a very zoned zircon, so each layer has a different age, and because of the small sample size of the SIMS, they were able to measure the very inner core, which resulted in an age of 4.4 billion years old. So this indeed is the oldest known fragment of Earth. And to further conclude on this, what's really interesting is that John Valley and other scientists were able to measure oxygen isotopes across this zircon grain, and the resulting oxygen isotopes provided evidence that perhaps surface temperatures were low enough to allow for liquid water on Earth back during the Archean. So this is a really interesting finding and one of the first evidence to support the theory that indeed early Earth had liquid water, which is pretty fascinating. So yeah, thank you all for listening to me talk about mass spectrometers. If you have any questions, feel free to contact me. Anthony knows my email. But yeah, I hope you all learned something and best of luck.